All right, so let's do another installment of analysis. So we're looking at section 8.3, subsection 8.3.3. And it's really, at this point, we're more looking at an interpretation of what we've defined rather than, really going to prove much. We're, more going to interpret, the derivatives in a couple of different ways that you've probably seen or that I'm pretty sure you've seen in vector calculus or calculus 3. All right. So suppose that you have a function defined on some open subset of the Euclidean space, right? So you could define a derivative, which is the linear transformation that approximates f, but another sort of version of the derivative, which in some sense is different, it's the gradient, right? And the gradient is simply you take the vector whose components are the partial derivatives. Now, this is, I guess, in some sense a little bit wrong. It's not, or it's wrong to think of it as the derivative, because the derivative is really the linear function, right? There's not quite, this is a vector, right? So a linear function, the derivative, if you represent it as a matrix, it would be a row vector, whereas here it's probably, you're thinking of it more as a column vector, right? So it's kind of a different thing, but it's the vector given by the derivative. Anyway, we can, since when we're doing dot product, well, I mean, it's sort of like taking the transpose of one vector and applying it to the other vector. So in that setting, the derivative applied to a vector is just like the dot product of the gradient with the vector. So it's essentially, in some sense, it's the same thing. It's just sort of, it's instead of a linear mapping, it's a vector, right? But it's a common notation to use, common quantity, and it has some geometric geometric interpretations that you've surely seen in vector calculus or calculus 3. All right, so now let's sort of so let's, if I have a function, a real valued function, right? So otherwise, this gradient doesn't really make that much sense, because it's otherwise I have sort of too many f's, right? If it's vector valued, so it's going from Rn to R, right? But we could also do the opposite, right? We could go from R to Rn, or really, some open subset being, some interval, right? So let's suppose that we have a gamma. It's a differentiable function, right? A lot of times, when we write down such a gamma, we call it a curve or a differentiable curve in this setting, or sometimes a path. So why is that? Well, because at each point over here, right, you could think of that as time, right? And then this is just telling you a position in Rn for each point in time, right? And so if you trace out the values, it looks like a curve. There's an example over here, right? This is when we're, I guess, at A and this is where we get at B, and this is the the inside. So let me get rid of these things. So if I have that, it's all functions of one variable, but now I have more components, right? So it has n components for this n, right? Now there is a when looking at such a gamma, I mean, if we took the derivative here, we should get. Well, I mean, if you think of it as a matrix, you actually do get a column vector. It should be a linear operator from R1 to Rn, right? From R to Rn, thinking of R as a vector space. So that is a column vector. So we could really think of it both as the operator over here and as a vector in Rn, right? Which is just this, this vector of the one variable derivatives, right? Thinking of all of these as numbers, right? Just standard derivatives from Calc 1, right, or from last semester. So really, we're sort of doing this sort of identification of this, and we're also identifying linear operators on R1 with R like before. So when you have a 1-by-1 matrix, you just think of it as numbers. And in here we're doing if we have R1 to Rn, well, we just think of it as vectors. So here it's not really changing anything. It's sort of interpreting, and unlike with the gradient where we had a it sort of is a different thing. A row vector, column vector are different. Here, it's the same thing, right? It's just interpreting it in a different way. All right, so let's move this up. Right, so we have this this curve. Now, what is how do we interpret gamma prime is a vector? It points somewhere. You want to think of it as the tangent vector to this curve. It points along the curve. Sorry, let me try to get right. So that's sometimes used, this interpretation as a tangent vector, right? As you're moving along, it's sort of telling you the direction in which gamma is moving, right? Now. Let's try to, so now we have, if we had an f and if we had a gamma, well, we could put them together, right? So if we had a function and we had a curve, we could compose these two, and we get a function of just a real valued function of one variable, right? And so this function, because both f and gamma, if we assume that these are differentiable, then g is differentiable, right? And just as I said, I'm identifying the linear operators on R1 with R, right? It's 1-by-1 matrices and the real numbers. So in that case, applying the chain rule, right, that we just proved, you get this, this expression. Well, let's just write it down what it is, right? and it's this dot product over here, right? Or if you don't write down the points, right, it's this guy, right? Right, and we often leave those out. Now, that dot product, if I write it down in yet another way, if I write it out as a dot product, it is actually, and again, with the points, without the points, it's the gradient dot gamma prime, right? So it's so we're basically taking the dot product of the gradient of f and the tangent vector of gamma, right? And that's how f is changing as we're moving along this curve. That's the interpretation here, right? That's the rate of change of f, right? That's g prime here, right? And it's given by this formula. So one of the things that you can do with this is to think, well, I mean, with the partial derivatives, we were differentiating in a specific direction in one of the principal directions, right? If we use standard basis on Rn, so we were differentiating in the x1 direction, in the x2 direction, x3 direction, and so on. Well, if we're interested in rate of change of f, maybe we can use this formula to. I mean, we can talk about rate of change in any direction, right? I mean, if I have if I'm in R3, right, and maybe F is the temperature, I want to see how is it changing as I'm moving, right? There's no sort of standard basis vectors in our universe, right? It's an arbitrary choice, but I might want to know how is the temperature going to change as I move in various directions. So let's think about that. So what we could do is we could instead of EJ as we had before, we could take any U which represents a direction, which really just means I'm going to take a vector of norm 1, and so just like the EJ, right? When I did it in the jth direction, I used EJ. So here I'm using U, right? And all right, maybe I'll highlight this thing. And then that was the definition of the derivative, in that direction, right? Instead of if it was the dfxj, right? It would be precisely, it's instead of u, it would have an ej in here, right? So it's almost like a partial derivative, but now in terms of arbitrary direction. This is just another way of writing down the same exact thing. If I think of moving along, in U using this curve, right? I'm going to define over here. Then and composing, so it's f composed with gamma, if this is the gamma, right? Then it's just the derivative, right? This is exactly the same thing. That's just writing out basically by definition what this derivative is, right? So right. So again, you can see that this is this notation over here, the d sub u. Well, it's the same as the partial derivative if u is ej. Now, sometimes people use this notation because of that, right? Df du, if you want to just indicate a direction, right? So All right. Well, if I think of this expression over here as, using this formula over here, you notice that basically the directional derivative in the u direction of f, well, it's the same thing as taking. So here, when t is 0, I'm precisely at the point where I'm trying to take this derivative, right? So that's why I'm plugging in gamma 0 over here. And so I'm taking the gradient of f at the right at the right point, and I dot it with the tangent vector, which is going to be u, right? If I differentiate this, I just get u, right? So that's another way of thinking about this, right? And this will, this formula works for any gamma where gamma of 0 is the point x, and the gamma prime of 0 is u, right? So it doesn't necessarily have to be this gamma, right? There's just one of them that will work. So you could think of it as the directional derivative. You could think of it as the derivative along a curve, right? The rate of change along a curve with that tangent vector. All right. Now, once we have this equation over here, well, we can apply Cauchy-Schwarz. Note that u is of norm 1, right? So what we get is, if the absolute value of the dot product, which is this thing, is less than or equal to the norm of this times the norm of this. The norm of this is 1, so just the norm of the gradient, right? So the Cauchy-Schwarz tells us that the directional derivative is bounded by the norm of the gradient. So the gradient gives us, its norm gives us sort of the maximal rate of change in any direction. Now, furthermore, Cauchy-Schwarz also tells us when is equality achieved, and it's achieved precisely when these vectors are scalar multiples of each other, right? When u is a scalar multiple of the gradient of f, right? Well, when is that, right? I mean, it's a unit vector, right? So I just look at the unit vector in the direction of the gradient, right? That's this, right? So I mean, you also get another place where equality will happen because of the absolute value signs, right? Is at minus u, right? I look at the other scalar multiple that is still a unit vector, right? But anyway, let's look at u at the unit vector in the direction of the gradient, right? So in that case, we get this equality with the positive, right? Positive sign. So minus u would get us a negative sign, right? Over here, right? So that means that the direction of the gradient gives us the largest rate of change, right? So the function grows the fastest in the direction of the gradient, right? So that's the interpretation of the gradient, right? The gradient is the direction in which the function grows the fastest, and its norm is that maximum rate of change, right? So it's kind of geometrically telling you how does the function change, right? So that's the interpretation of the gradient. Okay, let's also, let's not split this up into separate lectures. Let's talk about the Jacobian. Again, there's not much that we'll actually prove. It's more just sort of talk about the interpretation of something. So let's suppose that I have a differential mapping. So now, again, I'm back to Rn, and I'm actually going from Rn to Rn, right? So this is an equidimensional mapping, meaning that f prime is a square matrix, right? If I think of it as a matrix, right? Its determinant is so-called Jacobian determinant, right? Sometimes f prime is called a Jacobian matrix, I guess. So the Jacobian determinant is the determinant of that. Now, a lot of times when people say Jacobian, they actually mean Jacobian determinant. So sometimes if you just hear Jacobian, you have to think about: are you expecting a matrix or are you expecting a number? If you're expecting a number, it's the determinant, right? And a lot of times it is the number. So that seems to be sort of very common, very common usage. So we'll write it as J sub f, right? And it's really, that's just what it is. Now, sometimes this is written in this funky way. Which at first seems a little odd. You're sort of listing the components of f and listing the components of x, and it's not. You sort of almost think about this being, it's so sort of almost looks like, oh, maybe I mean the matrix. No, we mean the determinant. That's just the notation. So this is always going to be a number, right? Whenever you see this somewhere. Now, the reason for doing that is that that allows you to write down to, if you only want to pick certain, certain variables. So if you're going to fix some variables and just, consider the function in terms of just some of the variables, then this allows you to do that, right? Or you can pick just some of the components, or maybe you can, think of different functions as in terms of different, as components of a single mapping, stuff like that. So, right. So that's the notation for the Jacobian, right? And so that's just. This is just saying what I just said. It will be useful in the implicit function theorem, because then it's not going to be there we're looking at the determinant of a certain submatrix of the derivative, and this basically lets you specify the submatrix that you're looking at. Right now, if you're in one dimension, then the determinant of the matrix is just, if it's a 1-by-1 matrix, right, the determinant of the matrix is just that entry, right, that one entry. So it's simply the derivative, right? So there's sort of, in one variable, it's exactly the same thing. Now, one neat thing about the determinant is that it's multiplicative, right? So the determinant of A times B is the determinant of A times the determinant of B. So what it says about the Jacobian, right? Remember by chain rule, the derivative the derivative of the composition is the composition of the derivatives, and so its determinant is just the product of the determinants of the derivatives, right? So the Jacobian determinant of the composition is just the product of the Jacobian determinants of the derivatives. Now, as I mentioned a couple of times before, determinant basically tells you something about what happens to area or volume or the n-dimensional volume or length or whatever in like what does the linear mapping do, right? In terms of that, right? So if the determinant is 2, and let's say it's R2 to R2, right? So it's things with areas, right? So if you have a linear mapping from R2 to R2, and the determinant is, let's say, 2, then it doubles all areas. If the determinant is a third, then it takes all areas and so takes some shape, right, and maps it into a shape that's 1/3 of the area, right? Now, if it's -5, it will, what it will do is it will take every shape and it will map it to a shape of area 5 times as large, but it will also flip orientation. So whether the determinant is positive or negative tells you about orientation, what happens to the orientation, and the absolute value of the determinant tells you what happens to area. So this is basically, this is, sort of saying that sort of what happens infinitesimally to, a differentiable mapping, right? So it's if you have a differentiable mapping, then infinitesimally it sort of looks like its derivative, and it's saying, if it's infinitesimally, if you have a composition of 2 such mappings, and one of them is stretching by one factor and the other one is stretched by another factor, then the composition is stretching by the product of those two factors, right? I mean, in some sense, we're not really sort of proving anything. It's just this fact about linear mappings, right? It's just, at this point, it's just notation, right? So, but that's the interpretation of the Jacobian determinant, right? Well, it's just like the interpretation of the determinant, right? But for differentiable functions, the Jacobian determinant tells you sort of, if you really, really zoom in, what it will do with with areas or volumes or whatever dimension you're in, right? If you're in 3 dimensions, it's 3-dimensional standard volume. If you're in 4 dimensions, it's 4-dimensional volume, and so on, right? All right, so that's it for section 8.3. So let me stop this. If I can get to it. Oops.